Hi, Vidya.
Hi, Professor Naresh. Is the connection okay there?
Yeah, not bad.
Yeah,
A bit of rain this afternoon, so hopefully
I see.
it wouldn't affect the connection.
Yeah, because I saw just now you're still connecting. So yeah.
Yeah. Should be all right now. I think once it's connected, then it's fine.
Yeah, so actually we just finished a previous lecture on analytical chemistry using this Zoom account. So
okay.
Yeah, I just opened this. Yeah, because the schedule is from 1 to 2:40 Bandung time. So yeah.
Yeah, we can wait a few minutes for people to join, I think.
Yeah, still 30. Right. Okay. I sent you the graphical abstract.
Yeah, I got both of them, so we'll use one of them, I think.
Yeah, because
smaller one.
Yeah, because
yeah, and then the supplementary file and the slightly adjusted manuscript, you will send it at some stage.
Yeah. So I'm extracting the link that you sent to me because apparently it contained a lot of spectra, not only the proton or carbon, but also the IR and the MS as well. Yeah,
we can leave that in if you like, or whichever is easier for you to do.
Yeah, because apparently I put a lot of some notes on the spectra, so I need to remove. Yeah,
All
but
right.
it's I still can process it. So
okay.
I'm trying to remove all the notes.
That's right.
Selamat sore, Prof. Asep.
Selamat sore, Bu Vidya. Good evening, Prof. Naresh.
Yeah. Hi, Asif. Hi, Shalihan.
Hi, Naresh, how are you?
Good.
Good. Well, see you very.
Yeah.
Okay.
Yeah. Today is a bit warm actually, so I took my jumper off.
Oh, is it? Oh, yes. You're getting summer, is it?
Yeah, that's right.
Yeah.
But it's very strange weather at the moment. It gets cold and hot in the same day.
Yeah. No, Indonesia has become hot because eruption. Eruption. Semeru.
Dan medialis Vidya serta Ostapela.
Waduh panjang nih kan, sebenarnya.
Sela sendi mulai menyempit
Bu Amel, mangga.
Hi.
Okay, Bu Vidya, thank you. Shall we start?
Yeah.
Thank you.
Okay. Good evening, Prof. Naresh, and good afternoon, everyone. Bu Gebi, Pak Asep, Pak Hayat, and Bu Vidya, and all of the students. Today, we meet again in this lecture with Prof. Naresh. And Prof. Naresh, we will continue the explained about the alkene. Yeah, yesterday Prof. Naresh already explained about the nomenclature, structure, isomer, and also some of the reaction. And today Prof. Naresh will continue about the alkene reaction. And maybe after that, Prof. Naresh will continue to the lecture about alkyne. Right, Prof. Naresh. So for all of the students, if you have any questions related with the lecture, you can write in the chat box, or you can raise hand, so you can directly discuss with Prof. Naresh. Don't worry, you can use a bahasa. Yeah. So maybe I or Bu Vidya will help to translate to the English. Okay, Prof. Naresh, it's already 2:44.
Yep.
Yeah. Maybe this.
Okay. I start sharing my screen.
Yeah.
share. All right, and I just make it full screen and I grab a pen. Okay. All right, selamat sore, everyone. We're gonna continue today on the reactions of alkene. As it was mentioned in the introduction that in the last lecture, we concentrated on reactions of alkenes with hydrochloric acid, hydrobromic acid, hydroiodic acid, and we saw how alkenes undergo electrophilic addition reactions with HX. We can call that just general term. We also came across the concept of getting chiral center in the addition of HBr and HCl and HI to the alkenes. And that concept or that kind of enantiomeric structures are going to come again when we look at reactions of, say, for example, halogens like bromine, chlorine, and so on. But initially, we're going to start with the addition of water to the alkene. So the only difference between addition of HCl, for example, to alkenes versus addition of water is that instead of getting a halogenated product when we did the reaction with HCl or HBr, we're going to get a hydroxylated product. So if water is represented as HOH, similar to say HCl, in the HCl addition case, we added a chlorine and a hydrogen to the double bond. But in the case of water addition, you're going to add a hydrogen and a hydroxyl. So the ultimate product is going to be an alcohol in this case. But the interesting thing is, if you just take water and alkene and mix it together without any acid, you won't get any reaction. So water and alkene will sit there and sit there and sit there, and there'll be no reaction. This reaction requires catalysis by a mineral acid. So it means you need some sort of dilute HCl or dilute sulfuric acid to start the reaction. That means you need a catalytic amount of something called H+. We need that to start this reaction. Otherwise, water would not react with alkene by itself. And the reaction is practically useless, practically very, very slow if there is no catalyst present. But this reaction is very important industrially. This reaction is actually used in the industry to produce alcohol, ethanol. If you take a simple starting raw material, ethylene or ethene, and you reacted water with water in the presence of dilute acid, you generate ethanol. So this is a commercial process for producing ethanol in industry, because as you know, many cars, they can run on ethanol now. You don't need petroleum products. You can even use ethanol in the car. And that's how in industry, some of the alcohol is produced by reacting ethylene with water in the presence of an acid catalyst. So what is the mechanism of this reaction? How does this reaction works? We said the acid is important. So what does acid do is acid reacts with the alkene first. As we saw in the case of HCl and HBr, the H+ reacts with a double bond first. It adds onto the double bond to give a carbocation. So the first step is addition of a H+ to the alkene, or this process is also called as protonation of the alkene by the acid catalyst. It looks from this reaction as if the acid is consumed in the reaction, but we will see later that this acid is a catalyst, because catalysts don't get consumed in the reaction. Catalysts get recovered at the end of the reaction. So we'll see that if that happens. But the first step is the addition of H+ to the double bond. So once the carbocation is generated, we have lots of water present in our reaction mixture because we are using a dilute acid, and in the dilute acid, the majority of solvent that is present is water. And water has, oxygen has lone pair of electrons. So that means this can act as a nucleophile and attack the carbocation to add on to that carbon over there to give you this OH2 plus species. And this species then lose an H plus to give back the catalyst which we used in the reaction. So that means the protonated, we call that a protonated alcohol. It's just simply an alcohol which is protonated, because alcohol is simply this structure. You have oxygen and a hydrogen, that's your alcohol. And if you protonate that oxygen of the alcohol, is called protonated alcohol, and it just has a positive charge on oxygen, and oxygen will be happy to take that pair of electrons and kick the H plus out. So the protonated alcohol loses a proton to give you the alcohol as a product, and then H plus is liberated back in the reaction. So it's not used up, it's produced again in the reaction, and this can then react with other alkenes which is present and then give you the alcohol product. But this proton may not be the same proton which we used initially, because if you look at this reaction here, the proton we used here was from the acid, that's blue color. And the reaction we did with the water is black in color. So the proton that is liberated here is the proton which came from the water, although we added the proton from the acid, but the proton that is liberated is from water. But you can't differentiate the two because H plus is a H plus. It doesn't matter where it comes from, but it is not consumed in the reaction, so you get it back, okay? So this is the formation of the alcohol, or the reaction of water with double bond. We talked about the reaction of HCN already in the last lecture, so I'm not going to talk about this now, because we learned in the last lecture that HCN doesn't react with the alkenes because HCN is a very, very weak acid, and HCN doesn't dissociate into H plus and Cn minus sufficiently to be able to react with an alkene. Even if you use an acid catalyst in this reaction, because there is no Cn minus present, that reaction cannot take place. So that's what I was trying to say in the last lecture when we were talking about HCl, HBr, and HI, that they can act to the double bond. Even water can act to the double bond in the presence of acid catalyst, but HCN cannot. Okay, that's enough about water. Now we're going to look at another important reaction of alkenes, and that is reaction with halogens. XX can be a bromine, it can be a chlorine, but it can't be an iodide, because iodine, if you look at iodine like that, the reaction is reversible in the case of iodine, and thermodynamically the product is not favored in the reaction of iodine with the double bond. So we're going to mainly talk about reactions of bromine and chlorine with the alkenes. Now, how does the reaction happens? First of all, what product do we get when you react, say, bromine with a simple carbon-carbon double bond called ethene or ethylene? So what happens is you're going to get addition of bromine onto the double bond. So you're going to get a extra bromine on one carbon and extra bromine on the other carbon. So you're going to add two bromines to your double bond to get a dibromoalkane compound. Similarly, the reaction of fluorine with double carbon-carbon double bond is a very complex reaction, because fluorocompounds are not easy to handle, and fluorine gas is not easy to get hold of. So we're not going to look at reactions of fluorines either, because that's quite complicated reactions of fluorine with the alkenes. We're going to mainly look at bromine and chlorine. And iodine, the reaction iodine is not thermodynamically favored. That means the iodo compounds that are formed, they are not very stable. And it is also a reversible reaction in the case of iodine. So mainly the reaction which is of use here is the reaction of bromine or chlorine with the carbon-carbon double bond. And we're going to also think about the stereochemical consequences of the addition. And what do we mean by that? There are a couple of possibilities. One is when the bromine attaches to the double bond, it can either give you a what we call a cis product, or it can give you a trans product. And that's quite relevant when you got a cyclic alkene. If you have a non-cyclic alkene, say for example, if we just look at the example we looked here at the ethylene reacting with bromine, we can't really get a cis and trans isomer in this structure because there's a freedom of rotation between the carbon-carbon double bond, and the two carbons, they have the same substituent. There's a hydrogen, there's a hydrogen, hydrogen, hydrogen. So there's no chiral center in the molecule. So that means we can't really get any isomers with the simple alkenes reacting with bromine. But when we have a cyclic bromine, a cyclic alkene here, and we add bromine to that, there are two possibilities. One is that the two bromines can be present away from each other or opposite each other, and same as the hydrogens, or you can have two bromines present on the same side, close to each other, same side. So the where the two bromines are away from each other, we call that a trans addition. It's just like cis and trans double bond we learned in the last lecture. This is called as a trans addition because the two bromines are away from each other. It's also called as an anti-addition as well. But for simplicity, you might understand trans means away from each other or opposite each other. That's why we call that this a trans addition. And the two bromines can be on the same side. And we learned when the two groups are on the same side, that's called a cis geometry. So this is what we call a cis addition or a syn addition. So there are two possibilities. One is giving you the trans product or trans addition, and the other one is a cis addition. So do we get a mixture in this reaction? That's the question which arises. And I can tell you the answer is no. You only get the trans product in this reaction. So then the question arises is that why do we get trans product in this reaction? Why we get only trans addition? Why don't we get cis addition of bromine to the double bond? And the answer to that question lies in the next slide. But I also want you to think about this carbon over here and this carbon over here. I want you to think about this carbon and this carbon. Are they chiral carbon? Do they have 4 different substituents attached to it? So if you look at this carbon here, there's a bromine, there's a hydrogen, and then there is a CHBr group, and on the other side is a CH2 group. So this carbon here is a chiral carbon. And similarly here, this carbon has a hydrogen, bromine, a CH2, and a CHBr. This is also a chiral carbon. So we got 2 chiral carbons formed in this reaction. So the other question which arises is, are we going to get a racemic mixture? Are we going to get a 50-50 mixture of 2 enantiomers, or we're going to get just 1 enantiomer 100%? So there are 2 questions. One is, why do we get trans addition? We need an answer for that. Second one is, there are enantiomeric products possible in the product. So the question is it an enantiomerically pure product, or is it a racemic mixture, or does it have a 50-50 mixture of the 2 components, 2 enantiomers present in this compound. So let's answer one question at a time. Do we get trans product? Why do we get trans product? There are essentially two steps in this reaction. One is there's going to be an addition of Br plus to form a structure. We call that a brominium ion. Just like the HBr and the water, we saw that it was H plus, which added to the double bond. Here, you get the addition of bromine onto the double bond. But the bromine can also react with the carbocation that is going to form to give you a cyclic structure. And I'll show you the structure of that in a minute. And you will see that that structure will look something like you have a sort of a dotted bond with the bromine over there. And it's like a three-membered ring sort of structure you will get when the alkene reacts with the Br plus. And then the second step on this reaction is going to be the nucleophilic attack of this Br minus onto that three-membered ring you have here to give you the dibromo product that is formed. But before that, you might ask that why molecules which are symmetrical, say bromine is symmetrical, that how this molecule here can have a positive charge on one side and negative charge on the other side, because they are two identical molecules, two identical atoms. So why do we get the bromine plus attacking the double bond? We're talking about bromine, but equally the reaction applies to chlorine as well. So let's see how that can happen. So the way this bromine becomes positive is what we call polarization of the double bond. So what happens is you got alkene, which is quite electron rich, and bromine also is quite electronegative, as we know. So when the two negatives, they approach each other, they start to repel each other. And when they start to repel each other, one end becomes more positive than the other end. So one becomes slightly positive and one becomes slightly negative. So the text here is, as the halogen, as the bromine comes closer to the double bond, because in order for bromine to react with the double bond, it has to get close to it. Otherwise, it can't react if it's sitting over there. It has to come closer to that electron cloud we have. So as the halogen comes close to the double bond, electron density, the electron density which is there, it polarizes that bromine, bromine's electron density, because bromine is also quite electronegative. So the negative start to repel each other. So one side of the bromine becomes positive and the other side becomes negative. So the bromine that is closer to the pair of electrons here, it becomes positive, and the bromine which is away from it becomes a slightly negative in charge. So if it becomes positive in charge, then it can react with the double bond to form that brominium species. So what happens is, so as bromine approaches the double bond, this Br here becomes positive, and it is attacked by the double bond because the double bond is electron rich. It likes Br plus, and it attacks the Br plus, and then the Br minus is eliminated from that reaction. But the bromine here can cyclize back onto the carbocation that is formed. I'll show you the carbocation in the next slide. But what is happening is the bromine reacts with a double bond to give you an intermediate brominium species. This is called brominium species. It's like a positive charge on bromine, and it's a three-membered ring. And the same thing happened with chlorine. You will get a chlorinium ion, which is positively charged here. But there is also Br minus present as well. Okay, so I'm going to divide that a little bit further. Instead of just showing you this condensed, concentrated cyclization to give you the brominium ion, I'm going to show you a one step at a time, make it a bit more simple. This is an oversimplification, but just to make it clearer to you what's happened, I have broken that step into two stages just to make it simple. So what I'm saying is that initially the electron cloud attacks the bromine, which is positive, and you get addition of bromine. Br minus is eliminated, and you form the carbocation. And now you can imagine that if the carbocation is formed, now that can be cyclized by the Br electron pair to give you the brominium species. So this is a gross simplification, just trying to make it as simple as possible for you to understand how that brominium ion is formed. How do you get that Br plus forming in that reaction? Okay, then the second step is just the formation of the cyclic brominium species. So this is the first step in the addition of bromine or chlorine to the double bond. And it gives you that brominium species. Now you can imagine that if that is formed, we also have this Br minus floating around, which was kicked out earlier. And that can either attack this carbon or it can attack this carbon over there. So it can attack two of those carbons in the manner shown on that slide. Okay, so what happens here next is bromide attacks the intermediate. This is a symmetrical carbon. There's a hydrogen here, hydrogen here, hydrogen here, hydrogen here. So it doesn't matter which way it attacks. It attacks the brominium three-membered ring from the side opposite to the bromine. What do we mean by that? So you've got this carbon-carbon bond, and bromine is sitting on top, forming a three-membered ring, and bromine is a big atom, so it's sitting over there. And when the new bromine comes in, when the Br minus comes in, it cannot come from the top because the top is already occupied by the bromine. So that means the bromine has to come from the bottom side because it's like a brick sitting on my hand, and I can't really attack it from the top. I can only attack it from the bottom. So that's what happens in the next step. The brominium ion is attacked from the side opposite to the Br, and the Br atom of the brominium ion shields one face. So one side is shielded, like a brick, but the other side is free, and the Br minus can come and attack from the bottom side. So that's why in the product, the two bromines are away from each other. It's called trans addition or anti-addition because their two bromines are away from each other. When this is a carbon-carbon single bond and it's not a cyclic structure, it doesn't matter because the carbon-carbon single bond has a freedom of rotation. So that means this single bond can rotate quite happily in the other direction. So you won't see a difference between cis and trans in a carbon-carbon single bond. You can only see it when it is somehow blocked from rotating. And that will become clearer in the case of the six-membered alkene ring. So what about cyclohexene? So the starting material for this reaction was a cycloalkene, which is a six-membered ring, and you have that as your starting material. And we reacted it with bromine. The first thing which formed was this cyclic brominium ion. And once that cyclic brominium ion is formed, then the bromine will come and attack from the other side of this Br plus from the bottom to give us the two bromines which are away from each other, which are trans from each other, or which are anti in addition. On the other hand, if you have bromine attacking this carbon over here, rather than attacking this carbon, and this molecule is symmetrical, so it's not going to make any difference whether bromine attacks from attacks this carbon or the other carbon, you're still gonna get the product, which is like an anti-product, which is like a trans product. So then the question arises is this product a racemic mixture, or is it going to be an optically active chiral product or enantiomeric pure product? One thing which is interesting is here, if I put a mirror in the middle, you will find that they are like mirror images of each other. You know, the bromine is here and the bromine is here. Bromine is a Y and bromine is a Y. So they're like a bit like mirror images. So they are enantiomers, but are they present in same amount? Because we learned in the last lecture and the lectures before that when two enantiomers are present in 50-50 amount, we call that a racemic mixture. So in this case, the product is a racemic mixture because you get 50-50 formation of these two enantiomers, which are mirror image of each other, and they're superimposable. They are not non-superimposable, they are superimposable. And they're present, sorry, they're non-superimposable, but they're present in 50-50 amount. So there is 50% here and 50% over there in this case, so that the product is a racemic product, 50-50 mixture of two enantiomers. I hope that is clear, but we will be looking at other examples of this addition and then try to guess what kind of product you will get from this reaction. So those of you who are really interested in stereochemistry, I'm going to give you an interesting problem. And the interesting problem is that if you have a cis-butene, that means if you have a molecule that is CH3 here, and then a hydrogen here, and a hydrogen on this side, if you take this molecule here, versus a trans-butene, which is similar structure, but one methyl is on this side and the other methyl is on this side, and one hydrogen is on this side and the other hydrogen is on the other side. I want you to add bromine to that and then see what kind of compounds you will get from that reaction, particularly from stereochemistry perspective, particularly from chirality perspective, because you will get chiral centers. When you add bromine across this double bond or across this double bond, you will get carbons which have 4 different substituents. And that means it's going to give you stereochemical isomers. And you should be, if you're really, really keen, you should spend some time and then try to see what product you get. And I can show you, I can give you the answer that in this case, you will get a racemic mixture, while in this case, you will get a mesostructure. And mesostructures are present in stereochemistry as well. And you may learn about that yourself. So this is slightly advanced, but if you are keen, try that yourself and see how you go with that. But if we continue with the addition of chlorine and bromine and try to do the chlorine or bromine addition in the presence of water or alcohol. So typically when you add bromine or chlorine to the alkenes, you use solvents like dichloromethane. The solvents which are like neutral solvent, they cannot participate in the reaction because they can't give away hydrogen or a chlorine in the reaction. So this is just like a solvent. But if you do the reaction, say for example, in water or alcohol, the oxygen on the water and the oxygen on the alcohols can also act as a nucleophile. So when you form your carbocation after the first addition of the Br+, the alcohol oxygen or the water oxygen can compete because it is also a nucleophile. And also, when you do the reaction in water or alcohol, the water and the alcohol is present in very large excess compared to the amount of bromine or chlorine in your reaction. So that means instead of nucleophilic attack of the bromonium ion by bromide Br minus, you can see products where the attack comes from water or the alcohol in your final product. So that means instead of getting the dichloro compound, you will get a chlorohydroxy compound or chloroalkoxy compounds in these reactions. And that's shown in this slide. This is water molecule, H2O, simple, humble water molecule. And this is methanol, an alcohol. And both these reagents, the oxygen has pair of electrons and it acts as a nucleophile. That means the brominium species we have, instead of reacting with Br minus, it can react with the water oxygen or alcohol oxygen. Because in a solvent sense, if you do the reaction in water or alcohol, these are present in much more excess compared to the reagent itself, okay? So if water attacks that carbon, you're gonna put a hydroxyl group there. So your molecule is gonna have a bromine on one carbon and hydroxyl on the other. But you can see that the addition is a trans addition still. It's not a cis addition, it's a trans addition. And similarly, if you have alcohol, the alcohol will add the same Y to give you a bromine on one carbon and OCH3. We call that group a methoxy group because it comes from methanol. So we call that group a methoxy group, METHOXY, methoxy group. So you have a bromine on one carbon and methoxy on the other in a trans manner. Okay, I think we covered there enough, but maybe I want you to think about what if we have a, say, a structure which has a CH3 on one side, a carbon and a hydrogen on this side, and a double bond CH2, say hydrogen here and hydrogen here, and I ask you to react that compound with bromine, what sort of product we will get? Will we get a racemic mixture, or will we get an enantiomerically pure compound, or will it give us any chiral center in the molecule? So if we attack that with bromine, the first thing you might get is the formation of that intermediate brominium species. So you will get a Br. I'm just drawing that to make it simple for you so that I can ask a question. So we make that species over here, and you have hydrogen here and a hydrogen here, and you have your CH3 over here and your hydrogen over here. So the question is, so the first question is, will we get optically active, or will we get stereoisomeric mixture in this reaction? So that's the question I'm asking. Say yes or no. Will we get a stereoisomeric mixture in this reaction? If the answer is yes, then put on the chat yes. If you think no, then put in. So will the product have a chiral center? Maybe I can just make it more simple. Will this product, when it reacts with the second molecule of bromine, will it have a chiral center? Will it have optical isomers possible in this reaction?
Okay. Ya. Jadi mungkin mahasiswa bisa menjawab apakah produknya ada pusat chiral atau tidak. Ya.
If it reacts with Br minus, will it give a optically active carbon?
Okay, you can type your answer in the chat.
Just say Y or N, just yes for
Just
Y.
say yes or no.
Yes or no question.
Yeah, yes or no question. Oke, nah, jika nanti diserang oleh Br min ya, ini akan menghasilkan produk yang chiral atau tidak? Oke. Jawabannya ya atau tidak, silakan.
So what I'm asking is that if we have a Br minus and it attacks that brominium species, say if it attacks here, will the product will have a chiral center? Will the product will have possible isomers, stereoisomers? So say if I say you get this CH3 and you have a hydrogen here already, and I attach the bromine over here, and then on that carbon over here, we're gonna get Br up here, and then, oops, sorry, Br up here, and then we're gonna have a hydrogen on this side and a hydrogen on this side. So my question was, does this product has a chiral carbon? Can this product have optical isomers? And the condition I told you in the last lecture was if carbon has a 4 different substituents, then it can have a mirror image, it can have optical isomers.
Yeah.
And if you look at this carbon over here, you can see that it has 4 different substituents. There's a methyl here, there's a hydrogen here, there's a bromine here, and then there's another carbon here. So this carbon here is your chiral carbon. That's the chiral center. While this carbon over here has got 2 of the same substituents, 2 hydrogens. So this carbon cannot have the chiral center, what this carbon does. Okay. So then the next question is, are we going to get a 50-50 mixture of this product forming, or are we going to get an one single enantiomer forming in that reaction? And the answer to that lies, I told you the bromine is sitting on the top and the other bromine is attacking from bottom. But you can have the reverse reaction also where the brominium is sitting at the bottom and the other bromine is coming from the top. So that means it's going to be a racemic mixture formed in that reaction. It's not going to be a optically pure enantiomerically pure compound. Is going to be a racemic mixture. Okay, doesn't matter. The next reaction, we saw the addition of bromine was a trans or anti-addition. What about the dihydroxylation of alkenes? Instead of adding 2 bromines, can we add 2 hydroxyl groups to the double bond? And this is what we call a syn or a cis dihydroxylation of alkenes. That means the 2 groups are on the same side, OH on the same side, hydrogen away from each other, away from the hydroxyl in both cases. And this reaction involves reacting the alkene with basic potassium permanganate solution. It's going to be a cold, dilute, basic potassium permanganate solution. And it results in the addition of 2 alcohols to the double bond. And these types of compound, when the 2 alcohols are present next to each other, we call them diols, 1,2-diol, or it's also called as a vicinal diol. When it's present on the adjacent carbon, it's called vicinal diol. And the stereochemistry of this addition reaction is what we call cis or syn addition. And to demonstrate it, the best is to use a cyclic alkene or cyclic double bond, and this is cyclohexene. And if you use potassium permanganate, cold and base, you get cis hydroxylation. How does it work? Why does it give cis? Why doesn't it give a trans product? Like the bromine gave a trans product, why does hydroxylation gives a cis product? The reason for the cis formation is that it is believed that the manganese, which is present in potassium permanganate, forms a complex with the double bond. So this is the structure of the MnO4 minus the permanganate, because potassium permanganate is KMnO4, MnO4. There are 4 oxygens, and potassium is, as you know, is K single plus, and the MnO4 is -1. And you can see there's only 1 negative charge on MnO4. And this MnO4 forms a complex with that double bond. So oxygen forms that double bond like that. So once that bonded cyclic structure is formed, and when this is hydrolyzed or this is broken down, it gives the corresponding dihydroxy compound. And we call this compound as a manganate ester. Is hydrolyzed. The manganese oxygen bond is broken. So this bond is broken, as well as this bond is broken, and you get the corresponding dihydroxy compound, or the di all formed in this reaction. Again, I want you to think about why you will get, or what will you get if you start with cis and trans butene in this reaction. So something to think about again. What I'm asking you is, if you have a butene which got double bond, and we talked about cis butene already before, the 2 methyl groups, so 2 hydrogens on the same side, and I want you to find out what product you will get from this reaction. So if there was a CH3 here and a CH3 over here, and you do a cis or a syn addition to this molecule, what the products will be, particularly in terms of stereochemistry, which you might get from these compounds. So that's an interesting problem to think about, and is something who people are interested in stereochemistry, they should look at that in a bit more detail and see what products they will get. Okay. The last reaction I think we want to look at is going to be the addition of hydrogen to the alkenes. We saw today the reaction with bromine, chlorine. We saw the reaction with dihydroxylation, where we added 2 hydroxyl groups to the double bond. And the third reaction we're going to look at is where we add hydrogens to the alkenes. So if you add hydrogen to the alkenes, what product you will get? So if we start with the simplest possible alkene, which is just ethylene or ethene, and then you react that with hydrogen and add hydrogen across the double bond. So what you're going to get is you're going to put a hydrogen here and a hydrogen here. So you're going to get a carbon-carbon single bond like we get before. And we're going to get a hydrogen here and a hydrogen here and a hydrogen at the bottom here. And the same on the other side, you're going to get basically what we call an ethane molecule, the saturated hydrocarbon compound. So you're going to hydrogen here and hydrogen here and hydrogen here. But the question arises is, are these going to hydrogens add in a trans or a cis manner? Is it going to be a cis addition or is it going to be a trans addition? And also the addition of hydrogens to the double bond is called as a hydrogenation reaction. Hydrogenation means you've added 2 hydrogens to your molecule. And alkenes will alkene can undergo reaction with hydrogen. But this reaction with hydrogen doesn't happen by itself. If you take hydrogen gas, add it to the alkene, and wait for the reaction to happen, you'll be waiting for months and months and months, and there'll be no reaction. It requires some sort of catalyst. And typically the catalyst that is used is what we call a heterogeneous catalyst. By heterogeneous catalyst, we mean that the catalyst is not soluble in your reaction. It's like a solid added to your solution, and it just sits there. It can be a powder, it just sits there. It does not dissolve in the organic solvent you're doing your reaction in. It's just a heterogeneous catalyst. It provides a pathway by which the reaction can take place. Look, if you add a catalyst, a heterogeneous catalyst, and hydrogen, then the reaction can happen with the alkene. And the catalysts that are used typically are palladium or platinum metal. So palladium metal stands for PD, is palladium, and platinum is PT, is platinum metal. And typically, these are used as finely divided powders. So you don't put a lump of palladium in your reaction or a lump of platinum in your reaction. You actually convert them into the powder form and you add to your reaction. And the reason for converting them into powder form is that you increase the surface area of the catalyst. And if there's a large surface area, then more hydrogen can absorb and more reaction can take place. If it's just a one big lump, then there's a less surface area for the reaction to take place. So let's now see how this reaction really works. Hydrogen adds to the alkene in the presence of a catalyst to give an alkene. That's what we learned in the last lecture. You take ethylene, you add hydrogen, you have a heterogeneous catalyst, and you add the two hydrogens in. But there are two stereochemical possible outcomes. So the two hydrogens can be on the same side, or the two hydrogens can be on the opposite side. So if I just write one hydrogen here, we add it and circle that a bit. And we have another hydrogen over here. Sorry, and another hydrogen over here. And we form that carbon-carbon bond. And the other hydrogen, if I just put it over here and make a little circle and say that this hydrogen is trans or anti to the other hydrogen. So there are two possible stereochemical outcomes. The hydrogen can add either on the same side of the double bond, or it can add anti or trans like we saw in the case of the corresponding addition of bromine or chlorine. So what do we get? Is there both product forms or only one product? The addition of hydrogen to the double bond always proceeds with syn stereochemistry, with cis stereochemistry. That means the hydrogens, they always add on the same side. So like the hydrogens here, this is your double bond. The hydrogens are present on the same side. The hydrogens are not present in the trans form. So that means the hydrogenation reaction or addition of hydrogen to the double bond, to the alkene, gives a cis or a syn product where the two hydrogens are on the same side. No trans product, but only the syn product. The question then also arises is that this carbon over here, is that a chiral carbon? It got a hydrogen, methyl, a CH2, and a CH methyl attached to it. So there are four different groups attached to that central carbon here. And similarly, there are four different groups attached to that carbon over there as well. So there are stereoisomers possible in this reaction, but the product you will get from this reaction will be a racemic mixture. It would not be a optically pure stereoisomer. It will be a racemic mixture. It will be 50-50 mixture of two products of the chiral centers which we have. So the similarity between the addition of hydrogen and the dihydroxylation is that both these reactions, they give a syn or cis product, while the addition of bromine or chlorine gave us anti or trans products. Hydrogenation gives us a cis product where the two hydrogens are on the same side. What is the mechanism? So why does it give us that cis or syn stereochemistry? Why does it give us that addition? The way this reaction works is, imagine these lines and this line over here is our catalyst. Catalyst is present in a powder form. This is palladium or platinum. And the catalyst can absorb hydrogen. The hydrogen gets absorbed onto the catalyst. So initially you can imagine that the hydrogen will come close to the catalyst like that because the hydrogen is HH. And then what happens is you start to get the bond formation between the catalyst and the hydrogen. When that starts to happen, this bond breaks down and you get hydrogen reactive species present on the platinum surface. And when the alkene comes, alkene also, the electron-rich double bond of the alkene also likes the metal, and it can coordinate or form a bond with the metal surface. And hydrogen is also sitting nearby. So what happens is, after alkene complexes to the catalyst surface, the hydrogen can attack the carbon-carbon bond, double bond, to form this carbon-hydrogen bond. And then the second hydrogen comes and form bonds with the second carbon to give us the alkane product. An alkane product doesn't have a double bond, so it cannot bind to the metal catalyst that strongly. So it's just cleaves off and then it runs away. And this one regenerates the catalyst. So the hydrogen atom transfers to the alkene because this is like an atom. It's not like a gas anymore. Transfers to the carbon-carbon double bond. And then the second hydrogen atom transfers to the second carbon to form alkane as a product. And the alkane dissolves from the catalyst and the catalyst is regenerated. But the hydrogen can only add from the bottom, can only add from one side of the double bond. So that's why you always get a syn or a cis product forming in this reaction. The two hydrogen will be on the same side. Okay, before I discuss the partial hydrogenation, let me ask you a question. If I take this molecule here, I'm going to draw a 5-member ring or a 6-member ring, it doesn't matter, but let's draw a 5-member ring and say that we got this compound as our starting compound, hydrogen here and a hydrogen here. And to make it a bit more difficult, I'm going to put an oxygen here as well. And then maybe I can put another CO on that side. And asking you that if we take this compound and treat it with hydrogen in the presence of palladium or platinum metal, which is your catalyst, so let's say palladium, what would be the product of this reaction? What product we will get from this reaction? And the other question I might ask is that, will we get a chiral optically active product in this reaction, or we will get a racemic mixture in this reaction? First of all, let me ask a question again. Will this reaction give a chiral center after the reaction? Yes or no? If I do a hydrogenation of this compound, will the product be have a chiral carbon? Will it have a chiral center after the reaction? So I'm still waiting for the answer. Sorry, we'll just go back. Yes or no is the answer I'm looking for. I'm writing another question for you while you're thinking. I'm going to also ask what will be the product if we take the same compound and react it with, say, HBr or maybe bromine, what product we will get. So first question I'm asking is, will that reaction, will these two reactions, both reactions I've written down, give a carbon in the product which will be chiral?
Yeah. Okay, Prof. Naresh. Yeah, for the student, you can answer the question from Prof. Naresh. You can chat the yes or no. Jadi pertanyaannya dari dua senyawa ini ya. Yang pertama itu direaksikan dengan H2 palladium, yang satunya direaksikan dengan brom. Itu apakah ada C chiralnya gitu. Ya. Oke. You can say yes or no. Nggak apa-apa salah ya. Yang penting coba kira-kira ada nggak C chiralnya. Okay, you can say you can write the yes or no answer in the chat.
Don't be shy.
Don't be shy and don't afraid about the wrong answer, yeah.
Yeah,
okay.
No worry about wrong answer.
No.
So we got no.
No. Okay.
Okay, so we got two no. Anybody want to say yes?
Yeah. Just two from 79 and another abstain. Okay.
So
yes.
We got at least one yes. That's good.
Yeah. Okay.
So we got at least one yes. So we got more yes now as well.
Yeah. Yeah.
Let's
three.
have a little bit more vote. I got 3 yeses
okay,
and 2 no's. Anybody else want to give their opinion?
Ya, mungkin ada yang mau menjelaskan, menyampaikan pendapatnya.
1 more minute while I drink some water.
Yeah. Okay. While Prof. Naresh have a tech break, you can say your opinion. Why it is no, there is no chiral carbon, or why it is yes. Ya, boleh menyampaikan ya. Dengan bahasa juga boleh.
All right, we got 4 yeses, I think, and 2 no's. Okay, so let's see what happens. Okay. If you add hydrogen to this molecule, and we know that hydrogen will add from the same side, it will be like just like a cis or syn addition. So one hydrogen will go to that carbon and one hydrogen will go to that carbon. Okay, so that means the product we will get will be something like this. Oxygen, double bond, oxygen, because that is not gonna react. So you're gonna put, if I just draw it single bond here, and you have a carbon here which has a hydrogen, hydrogen over here, and we added another hydrogen over here, right? So this is our coming from hydrogen, and then we added one more hydrogen here because the double bond is gone, and we added that syn addition. Now look at this carbon here. This carbon got 4 hydrogens, so it's just like a CH3 group. So this carbon is just like a CH3 group, and if it's a CH3 group, there is no chiral carbon because all 3 hydrogens are the same. But if you look at this group here, this carbon here, the one where I put a star, on one side we have a hydrogen, on the other group is methyl group, other group is oxygen, and the other group is a CH2 group. So this carbon here has got 4 different substituents, And if it has 4 different substituents, that means this is a chiral center. This is like a chiral carbon. So that means there are enantiomers possible in this reaction. And similarly, if you look at the addition of bromine, we are adding bromine in this case, and the bromine is going to add in a syn or anti manner. So we're going to have one bromine going up and one bromine going down, because we know that it adds in a syn or an anti manner. So the product in this case is going to be, you're going to have, say, a carbon here, and then you're going to have a carbon with a hydrogen over here and a hydrogen over here, and you're going to have a bromine sitting at the top, and you're going to have a bromine sitting at the bottom. Okay, and if you look at this carbon here, this has 2 groups which are the same, hydrogen, 2 are hydrogen. So if 2 groups are the same, then there's no chiral center here. But if you look at this carbon over here in the middle, you will see that it has 4 different substituents. Got a bromine, got oxygen, got CH2, and it got a CH2Br. So this group is different from this group. So that means this carbon here is a chiral carbon. So both these reactions are going to give you a product with a chiral carbon. So my next question then is, are these products going to be racemic mixture? These 2 products here, which we formed by hydrogenation and bromine addition, are they going to be racemic mixture, or are they going to be optically pure enantiomers? So again, I'm asking for yes or no answer. Are they going to be racemic? Then you say yes. If you think they're not going to be racemic, they're not going to be 50-50, then you should say no.
Okay.
So again, yes or no? Is it going to be racemic mixture or not racemic mixture?
Yeah, another yes or no question. So, jadi pertanyaannya tadi sudah ya, dia terbentuk chiral, kemudian dari kedua produk ini apakah bisa terbentuk racemic atau tidak? Okay. You can say yes or no in the chat box. Jadi apakah nanti produknya ada racemic? Racemic itu berarti campuran ya, atau dia pure? Okay. You can write it. Boleh ditulis.
Racemic.
Racemic.
We got one
Okay,
racemic answer.
one racemic. Yes, itu okay. Racemic.
Yep. Good.
Yep.
Looks like we got agreement, at least from 2 people, that it is going to be racemic.
Yeah. Okay.
Okay.
It's 3 people.
3. Okay. We got 3 now, so that's good. Yes,
Okay.
the product is going to be the racemic product, because the hydrogen can add from the bottom or from the top. It doesn't matter, because when the hydrogenation happens, this double bond can bind to the metal surface either this way or that way. It can bind either way. It doesn't matter. You can't stop it from binding in this way or that way. So it's absolutely identical. And then the hydrogen can add on the same side, and you will get a racemic 50-50 mixture of the 2 enantiomers. And the same with the bromine here also. The bromine is little tricky, but we can see what the intermediate is going to be first. So that first intermediate you will get from the bromine reaction will be that you will form a brominium species like we learned before. You're going to get a Br plus forming in that reaction like that. And you have a hydrogen here and a hydrogen here. So that's your first species that is going to be formed. And then the Br minus can come and attack your, say, this carbon over here to give you the corresponding product. which I have drawn over there in this manner. Okay. So that will be your product. But the other possibility also is you might say, why doesn't, or what will happen if this Br minus attacks the other carbon? Say if I just write dotted, 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 dotted this time and attack, say, this carbon over here and move that across over here. So your product you will get will be very similar in that reaction. So you will basically put the bromine here and the other bromine will go up there. So it's pretty much the same in both cases. So the second product that is possible is double bond, and you are attacking the bromine from the bottom, and then you can have your carbon. Sorry, I should have drawn it the other way around, but that doesn't matter. Hydrogen here and hydrogen here. So you get it like this. Sorry, the bromine is up here like that. But that's the same as that structure. Actually, I should draw the other structure for you to make it a bit easier. So I'm just gonna take the eraser and just rub a few things here so that it becomes a little clearer as to what is happening. So we're gonna take the pen back if I can. Yeah, and I'm gonna put, say, so this was bromine already at the bottom. Sorry, take a razor, rub this off, and rub this off for the time being as well. Rub the chiral center as well, and take the pen, and then I'm gonna write. So we are attacking. If the bromine attacks over here, right? You get a bromine coming this way and the bromine going up that way. And if you attack bromine over there, you get bromine down here like that, hydrogen over here, and the other bromine shows up over here like that. So it's just a slightly different way of drawing it. So if the bromine attacks there, this will lead to this product, because bromine, no, sorry, what I'm doing, must be late. Just take the eraser again, just try to rub that off again and take the pen. Okay, so if bromine is attacking from the bottom, that will move up there. So this is this arrow going that way. Okay, I'll make this bold so that you know that the one which is bold over here is going in this direction. Bromine comes down and this bromine goes up because of breaking that bond. If you use the left-hand side over here, then the bromine comes here and the other bromine shifts over this side. That's the second product you will get. So you will get a 50-50 mixture of the two enantiomers in this reaction, and it'll be like a racemic mixture. So you have the answer correct, that the structure will be racemic mixture. Okay. Should I give you more question, or should we? Let's look at one application of this reaction. I'm just going to try to rub it off so that I can bring the next slide back, because otherwise the next slide is going to be all crowded with these structures I've drawn here, because you won't be able to see the slide. What I want to show you is an application of hydrogenation reaction in industry. And this reaction is very, very important from industry point of view. And it is used in production of a very important product, which we use every day in our cooking. I'm sure you would have used it today or another day. Let's just see if I'm still interfering. I just rub the rest off as well so that you can see this reaction. And this reaction is basically the reaction of an oil with hydrogen. And this reaction in industry is called as partial hydrogenation. Okay, this reaction is called as partial hydrogenation, not complete hydrogenation, but partial hydrogenation. And this structure here is an oil. And this oil can be cooking oil, can be canola oil, can be sunflower oil, can be any kind of oil. And this oil has got double bonds in it. This is an unsaturated oil. Unsaturated means it got double bonds. Some have 2 double bonds, some has 1 double bond. But one thing in these double bonds is that these double bonds are present as cis double bonds. Their hydrogens are on the same side. That's the natural oil. The hydrogens are always on the same side. So in industry, if you take an oil and start hydrogenating it, start adding hydrogen in the presence of a catalyst, and the catalyst in this case is a nickel catalyst, not palladium or platinum catalyst, a nickel catalyst, nickel metal. You will start to reduce these double bonds. That means you will start to add hydrogen onto that double bond, hydrogen onto that double bond, and hydrogen onto that double bond as well. But not all of the double bonds are reduced. We are only reducing some of the double bond. That's what we call it partial hydrogenation. So what happens is when the double bond starts to react or start to get reduced, you start to get the formation of what we call margarine. I hope you all know what margarine is. Margarine or even butter. But margarine is better because margarine comes from oil. And if you take oil and you hydrogenate the oil, partially hydrogenate, not completely hydrogenate, you will get butter-like consistency. You will get a product which looks like butter. You started with oil, you do partial hydrogenation, and what you got is a product which is like butter. And margarine, you can know your margarine, you can spread on a toast. You can make a toast and then spread margarine on it. That's how they make margarine in the industry. This is how margarine is made. You take an oil, cis alkene. Oh, there's a sound in it as well. And then that double bond is reduced, gone, double bond is gone, double bond is gone. This double bond is cis double bond still, but some of them double bond also becomes a trans double bond during hydrogenation. During industrial hydrogenation, some of the cis bond gets converted into the trans bond, and the double bond is only partially hydrogenated. So that's how they make margarine. You know, the margarine we get in the supermarket, which you buy to spread on the bread, it actually made from the oil using this hydrogenation reaction, reacting the double bond with hydrogen in the presence of nickel catalyst. Oops. Okay, I didn't make these sounds, so it was already in the slides. Okay, so that completes the section on alkenes. The next topic I'm going to talk about is carbon-carbon triple bond, which we call alkynes. So alkyne is a hydrocarbon that contains a carbon-carbon triple bond. That means a carbon is bonded to a carbon with a triple bond like that. So instead of having just a double bond, it got 2 pi bonds, 1 sigma bond, 2 pi bonds to form that carbon-carbon triple bond. And just showing you structures of 2 alkynes. One is what we call a terminal alkyne. That means the C triple bond C is present at the end of the molecule. So that means there's going to be hydrogen here, and then the rest of the molecule is whatever you want to call it. while this one here at the bottom is where the carbon-carbon triple bond is present in between carbons. So that means it's going to be something like this. Instead of a hydrogen, it has an R group. So here, the triple bond is present at the end. We call that terminal. And here the triple bond is present within the molecule, and we call that an internal alkyne, and one is a terminal alkyne. How do we nomenclature these alkynes? The nomenclature of alkynes is very similar to alkenes, but the only difference is at the end of the name, you will have Y and E instead of E and E. You remember that when we had a carbon-carbon double bond, we call that molecule as an ethene molecule. That means we call it, we called it ethene because it was a carbon-carbon double bond. So we call that ETH, ENE, ethene molecule. There was E and E at the back. Here we have Y and E at the back. So this is ethyne, or triple carbon-carbon triple bond. I will leave some time for questions as well shortly. I just want to cover a couple of slides on alkynes, and then we can have some time for questions in a minute. So the only difference is there's Y and E at the end. You again count the number of carbons that are present in your molecule, and you give the triple bond carbon where it starts the minimum number. So like this one here is a 4-carbon molecule, 1, 2, 3, 4. We start with carbon on this side. That's where the triple bond is. So 1, 2, 3, 4. This one is called as 1-butyne because a 4-carbon chain. So we call that a butyne. And if it's present inside the carbon chain, we try to give the carbon with the triple bond the minimum numbering. And that numbering is 2 if we start on this side, because if we start from this side, then it's going to be 1, 2, 3, 4, 5. So it's going to be like 3 pentyne. So this one is 2 pentyne because of 5-carbon chain, and Y and E at the end tells us that this is an alkyne. And if you have substituent attached, then you find the same way the longest carbon chain that is present with the triple bond in it. So if you start going this way, you find that the biggest carbon chain that is present in this molecule is the 6-carbon chain. And we want to give the carbon with the triple bond the minimum number. So we start with 1, 2, 3, 4, 5, 6 like that. Not the other way around, because if I start from this end, then the triple bond will get numbering which is 4 and 5 rather than the smaller number which is 2. So that means it's like a 2-hexyne. It's a 6-carbon chain with 2. Sorry if I just rub that mess I made. So if you just rub that off, and you will find that it is the 6-carbon alkyne chain. So that means it's going to be hexyne, 6-carbon hexyne. And then where the substituent is attached, the methyl substituent is attached at the 4 position, where it becomes 4-methyl 2-hexyne. So the nomenclature of alkynes is very similar to the nomenclature of the alkenes. So there's not much difference. Interestingly, again, for some people who are a bit more keen and a bit more interested, the group with a triple bond and a CH2 at the end, this group is called as a propargyl groups. That's a very commonly used group in organic chemistry. And when you got a corresponding double bond with the CH2 group, this group is called as an allyl group. And the corresponding compound, if you have a bromine here, is called as a propargyl bromide. And this one is called as an allyl alcohol or aryl bromide if there's a bromide here. So again, the nomenclature of the alkynes is very, very simple. Just like the alkenes, there's not much difference. You just put Y and E at the end. And the structure of alkynes is also very interesting. The carbon-carbon triple bond is there. And the interesting thing about the carbon-carbon triple bond is that this angle here is a 180-degree angle. So that means the carbon-carbon triple bond substituent are going to be like a flat structure. It's like a plane structure, flat structure. And the alkyne bond or alkyne group is formed by a sigma bond between the carbon and carbon. So there is a sigma bond present between the carbon and carbon. And then there are two pi bonds present in the carbon-carbon triple bond. So one bond is a sigma bond formed by the overlap of sp-sp orbitals, and two of the overlaps that are present by the p orbitals, these are what we call the pi cloud, which is there. And there are two pi bonds present in the carbon-carbon triple bond. But the thing to remember is that the four carbons or the four groups here are like in a straight line. And same here, if you got carbon, carbon, triple bond carbon, and a carbon, they will be all four in the straight line, like shown here. The bond between carbon and hydrogen is obviously just a simple sigma bond, but the middle bond is the triple bond. And the alkynes are going to be electron rich, just like the alkenes are electron rich. Alkynes are also electron rich. So that means they also going to react the same way, but two times with all the reactions we learned so far. They're going to react with HX, HCl, HBr, HI. They're going to react with water. They're going to react with bromine, chlorine. They're going to react with hydrogen. All the reactions we have learned of alkenes are going to be applicable to the reactions of alkynes, except the alkyne has got two pi bonds in it rather than alkene, which has one pi bond present. I'm going to stop here today and then have some time for questions. So how about we stop here for now? And I'm happy to answer any questions which people might have. And we'll finish the alkyne lecture next week when we meet again.
Okay, thank you very much, Prof. Naresh, for the explain about the addition reaction in alkene. Yeah, so maybe all of the students have the question. You can raise hand, or you can type your question in the chat box. Ya, oke. Adik-adik mahasiswa boleh silakan menanyakan ya tentang reaksi adisi tadi atau yang minggu lalu ya yang mengenai alkene. Boleh ditanyakan di chat box. Silakan. Boleh pakai bahasa Indonesia. Oke. Okay, maybe while we waiting for the, okay. Oh, yeah, there is two student raise hand. Oke, Fatimah, silakan.
Saya izin pakai bahasa Indonesia ya, Bu.
Iya, iya.
Jadi tadi di slide yang nomenclature alkaline itu ada terminal alkaline sama internal kalau nggak salah. Itu bagaimana kita mengetahui itu terminal atau itu internal yang tadi, Bu?
Okay, for the alkyne, yeah.
Yep.
Okay. So Prof. Naresh, Fatima asked about the how we can differentiate the internal alkyne and also terminal alkyne.
Okay, let me share my screen again so that we can see the slide. So the question is that if we have a terminal alkene here like this one butane has a terminal alkene, right? And this one is a internal alkene, so that's not terminal anymore. How can we differentiate between these two? So if I gave you a sample and ask you to tell me whether this has a terminal alkyne or not, what would you do? So one thing you can try is that we will do that later in the lecture next week, that this proton here in terminal alkynes can be removed. If we use a strong base, and an example of a strong base is sodium amide, is called NaNH2. It's like sodium amide, it's a strong base. Strong base can remove that proton. So that means what you will get from this reaction will be C triple bond C, and you will get a minus charge, and you will get sodium. And then you can react that compound with anything you like. Is like a nucleophile. So if I just put an R here, for example, and say if I have alkyl bromide, which is say CH3 iodide or CH3 bromide, then this will react with that methyl and kick out the bromide out, and you can do this reaction if the acetylene is terminal. But if the acetylene is in the middle of the molecule like this, it's like an internal acetylene, there is no hydrogen present on that carbon. So that means we can't remove anything. So if you treat it with base, nothing is going to happen and no reaction will take place. So we will learn about this reaction in the next lecture. And you can differentiate between the terminal and internal alkyne by doing a chemical reaction.
All right.
The other way also is, I don't know if you know NMR, I don't know if you learned about this technique called nuclear magnetic resonance spectroscopy. It's called NMR spectroscopy, where you can look at the proton and the carbon in a molecule by using this spectroscopy. This acetylene proton CH in a proton NMR, if you do a proton NMR spectrum, typically this signal will appear between 2 to 3 ppm. That's a typical standard value for an acetylene. It comes around 2.2, 2.3, 2.4 ppm in the proton NMR spectrum. So if you take your sample, run an NMR sample, you will get that signal if the acetylene is a terminal acetylene. Okay. Does that answer the question?
Okay, all right. Fatima? Okay. So, yeah, thank you, Prof. Naresh, for the answer. I think Fatima already get the answer. So
Yep.
the second one is Rafi. Hello, Rafi.
Yes.
Yeah.
I want to ask you a question, sir, but in second thought, I already answered my question, but I'm gonna ask it instead. So, sir, is there any difference between the Br molecule that attacking from like bromide, like Br minus, and the different and Br from like Br positive that having an atom shield? Is there any difference between that molecule?
Let me see if I understood your question. You're talking about alkenes, is that right?
Yes, sir.
If I just take you back to the alkenes bromine reaction. Okay, so the question is, maybe if we just look at one of the examples, maybe here. Oh, no, not this one. Maybe here. Sorry, you're asking that bromine attacking this carbon or attacking this carbon, is that right? Or
yeah, I'm asking about the Br molecule. Yeah, that two Br molecules are having like negative and positive Is there any difference between that molecule?
Oh, is there any difference between this Br plus and Br minus? The main reason why this Br is plus is that it got carbon bond Br and a carbon bond Br. It got two bonds to that Br. That's why the Br becomes positive. Because if you look at a simple Br molecule like CH3Br, for example, there's only one bond between carbon and bromine. So CH3Br looks like this. So you have a hydrogen here, hydrogen here, hydrogen here, and then you have a Br over here. So there is hydrogen here and hydrogen here and hydrogen here. So there's only one bond between carbon and bromine, so it's neutral. But if you form another bond between this bromine and carbon, then it's going to become positive, because bromine can only have one bond. If you put two bonds, then you're using another pair of electrons from the bromine to form a bond. So that's why this Br becomes positive, while this one is negative, because this is electron full, like the orbitals are all full to form Br minus, and that's where it can attack the bromonium species. Because you have, say for example, if you have HBr or Br, if you take away that pair of electrons, because a bond is formed between by sharing the pair of electron, and if you take that both pair away to Br, this Br is going to become Br minus, and this gonna become H plus, right? And the same thing applies to Br. If you take away a pair of electrons, it becomes like a Br plus, and if you give it a pair of electrons, then it becomes Br minus. That's the difference here. So this is plus, this is minus. This has an extra pair of electrons. This has one less pair of electrons.
Okay. Okay, Rafi, is it?
I'm gonna ask more. I think like in the product, like there is like in the red one there is a Br with red bond, and decided it's like Br with two atoms.
Yeah.
Yeah. So is there any difference between that molecule?
Between these two molecules? Yeah. So they are like mirror image of each other. That's why I put a mirror in between. If you put a mirror in between, you can see that these molecules are a bit like images of each other. So basically what's happening is that on one side, the bromine minus is attacking this carbon to give you this product. On the other side, the bromine is attacking this carbon to give you this product. So there are two possible products in this reaction, but chemically you can't differentiate them because they are exactly the same. You have bromine up, bromine down, bromine up, bromine down. In terms of physical properties, they are same compounds, but they are enantiomers. They are like mirror image of each other. And if they are mirror image of each other, their properties will be very similar. If you do NMR spectrum will be same, their reactivity will be same. The only difference is that they are like mirror images. They are like enantiomers, and they're present in 50-50 amount. That's why you get a racemic mixture product forming in this reaction.
Oh, okay, so it doesn't really matter if the mirroring, like this one is having like two atoms and the mirror is not having that two atoms.
Yeah, I think that doesn't matter. This is just a pair of electrons which is shown here, so that's not really anything to worry about.
Okay, so thank you, sir, for your answer.
Yeah. No problem.
Okay, thank you, Prof. Naresh, for the answer. Okay, there are any questions from students? Maybe one last question. Yeah. If there is no question from student, may I ask you Prof.
Yep.
Naresh.
Sure.
Okay. All right. I'm very curious about the lactone compound that you give earlier for the question. That is the racemic product, right?
Yep.
But I'm curious because the alkene is not symmetric. Yeah.
Let me just see. If I just go to.
I think you already erased it.
Did I erase it?
Yes.
So then I can draw it again, no problem. Okay, I did probably erase it. I thought I kept it, maybe I didn't. Okay. Maybe I just find some blank space. Okay, there's plenty of blank space here. So I think your question is that if we had that molecule, if I draw it quickly again,
yeah,
and a double bond, and you react that with bromine, was it?
Yeah, yeah. Okay, with bromine.
Yeah.
So, okay.
Yeah, and the product from the bromine which we drew was that it was double bond here, and you can put a bromine over here.
Yep. And
it's going to be an anti-product, so
yeah,
you can put the bromine at the bottom here.
Okay.
And then put hydrogen and hydrogen. Okay, so what is the question now?
Okay. So we all know that the bromine can attack from the top or the bottom.
Yep.
Yeah, but I'm curious, is there any effect from the lone pair of the oxygen? So can affect the presentation of the products. So maybe there is any major or minor products?
Yeah, that's a good question. Because, you know, the initial product, if you do the bromination, in this case is going to be, you're going to get a brominium species, Br, and then you're going to have, say, this one here as a positive, and then you're going to have a hydrogen here and a hydrogen over here, and then you're going to have that is not going to be affected. So the question is that somehow the bromine attack is going to be different compared to say here, or compared to over here. To the product, it doesn't make any difference, because if you attack on this side, you get the same product. If you attack on that side, you also get the same product. The only difference is that where the bromine is located. And once a carbon-carbon single bond is formed, there is a freedom of rotation in the carbon-carbon single bond. So you might put bromine at the bottom here, and you put the other bromine at the top, say bromine here, and then have your hydrogen over here and hydrogen over here. So there is no difference between this product and this product, because this is a carbon-carbon single bond. When there's a carbon-carbon single bond, it can rotate quite freely. So that means it can rotate quite freely. But the only difference between this structure and this structure is that this is a chiral center. And because this is a chiral center, these two molecules are going to be mirror image of each other. So they will be still present in 50-50 amount if there is no difference between the attack here and attack there. But you have a point there. I mean, what you're saying is that maybe this side is more hindered. Maybe, you know, it's more crowded compared to this side over here.
Yeah.
So maybe one side is preferred over the other to some extent. So you may get one more than the other. It is possible in this case, because you might get more attack on this side and less attack on this side. The product is going to be the same, but you might get one enantiomer present in more quantity than the other. That's possible.
Okay.
Yeah. But in most cases, you will get a 50-50 mixture.
Okay. Thank you, Prof. Yeah.
Okay.
Thank you for the answer. Okay, there is a question from Dewi Meliati. Okay, Bu Dewi. Okay.
Hydrogenation of carbon.
Reduction carbonylactone can be happen?
Yeah, that's a very good question. Can this carbonyl also get reduced? Because we learned when we were doing the carbonyl chemistry that the carbonyl group can also be reduced. But this carbonyl is present as an ester. It's not a ketone, it's like an ester. And esters don't undergo reaction with hydrogen. If I use a reducing agent like lithium aluminum hydride, I think we learned last time this is a strong reducing agent, lithium aluminum hydride, that can reduce the carbonyl ester, the ester from the carbonyl from the ester. But the hydrogenation, hydrogen and palladium cannot reduce an ester carbonyl. It can only reduce a carbon-carbon double bond, can also reduce a ketone if this compound was, for example, a compound which did not have oxygen, but had, say, carbon here and a carbonyl here. So this is like a ketone, and then has a double bond here, hydrogen here, and a hydrogen here. And if you do hydrogenation of this compound, there is a possibility that this will also get reduced. But when you have it as an ester, then it cannot reduce under hydrogenation condition. So good thinking, but because it's an ester, that's why it cannot react. But I'm glad you're thinking about it, that this could possibly react. Yeah, good.
Okay, thank you, Prof. Naresh, for the answer. Is there any question for all of the participant or student? If there is, okay, there is a question, raise hand from Syahrul Royhan. Okay, hello, Syahrul.
Oke, saya izin memakai bahasa Indonesia terlebih dahulu ya.
Ya.
Saya izin bertanya gitu, mungkin tadi saya kurang fokus atau bagaimana. Kenapa pada saat alkena itu bereaksi secara adisi dengan halogen itu, misalkan dengan bromin gitu ya. Nah, kenapa dia tuh terikat oleh dua karbon dulu gitu. Berbeda halnya ketika diadisi oleh sebuah
asam halida ya.
Iya, nah seperti itu.
Alright, thank you, Syahrul. Okay, the question from the Syahrul is about the why when the alkene react with the bromine, the first step is what is that? Make a bromine ion species, brominium. Yeah. But when the alkene react with the HX, or there is no brominium species. Why?
All right. Okay. All right. So the question is, if I just go back a bit, when we are saying that the bromine reacts, it forms the brominium species. We say we form that, right? So the question is, why don't we form, say, if instead of this, we said the brominium species is formed because, oops, I got too much mess here. Let me just try to rub it off. I just take the razor. So I just try to rub this off so that, because it's easier to explain here. I wouldn't rub all of it. I just rub this part here. So in the case of bromine attacking, we form the brominium species. So the question is, why don't we form with the hydrogen the same thing? So in the hydrogen, say,
excuse me, Prof. Naresh.
Yeah.
You already shared the screen?
Oh, sorry. I need to
You
share the
haven't shared
screen.
the,
Just
yeah.
1 second. Oops, hang on. Discard. Let me just go back to sharing screen. I think I forgot to share screen. Thanks for reminding me. It must be getting late here. Okay, so right, that's better. Okay, so I think the question was, can we, so just make it full screen again. Oops, sorry. Yeah. So the question was, why don't we form a species similar to that with H plus? So you got a carbon here, hydrogen here, and a hydrogen here. That why can't we form an H like that species? Is that correct? That was the question, right?
Yeah.
But this happened because bromine has a pair of electrons. So if you look at which hydrogen is the first atom or element in our periodic table, so it doesn't have that extra pair of electrons which are there in the case of bromine. So if you have this CH, this plus here, and you got hydrogen here, this hydrogen does not have that pair of electrons because it's the first element in the periodic table, so it only got one electron, so it doesn't have that spare electrons to form that ring. And this is not possible because you can't have hydrogen bonded to two carbons with a positive charge because it doesn't have that pair of electrons, and this will be very, very unstable, so it wouldn't form. Only the bromine, which has pair of electrons, can form that.
Okay.
Or chlorine, if you have chlorine, that can also form it, but not hydrogen, because hydrogen doesn't have that extra electrons.
Okay, okay. Thank you, Prof. Naresh. Is it clear, Shahrur? Okay.
Yes.
Okay, thank you. Yeah. Thank you, Prof. Naresh, for the clear explanation. And also thank you all of the students and also the participant for the question. So I think today we got a fruitful discussion about alkene and also alkyne. Okay, I think it's already 4:31 and maybe it's very late in the Prof. Naresh. We are so sorry for this. I think we can end this lecture today and we can continue for the alkyne in the last meeting, yeah, for next week. Okay, it's already last meeting with Prof. Naresh. All right.
Thank you.
Okay, thank you very much, Prof. Naresh. Have a good rest and see you next week.
Bye, Asif.
Thank you, Prof. Naresh.
Oke, baik. Terima kasih Bapak Ibu yang sudah hadir dalam perkuliahan ini. Masih ada Prof. Asep, Bu Gebi, dan Bu Vidya. Terima kasih. Kemudian kemudian kepada semua mahasiswa terima kasih ya. Bagus ya, sudah banyak yang bertanya nih. Minggu depan Prof. Naresh terakhir harus lebih semangat lagi buat bertanya. Ya, mungkin saya cukupkan sampai di sini pertemuan hari ini. Terima kasih untuk semuanya. Saya akhiri. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
warahmatullahi
wabarakatuh.
Ya, turnuhun Bapak Ibu.
Ya, Amel.